We use it every single second of every day, but do we really get how it works? I'm talking about electricity, of course. We all have a basic idea, but the reality is, well, it's way more fascinating and honestly, a little bit weird. Let's dive in.
So let's start with a really simple question. You walk into a dark room, you flip a switch, and poof, the light is on. Instantly. But what does instantly actually mean here? What is physically happening inside that wire in the split second between you flipping the switch and that bulb lighting up? Okay, so we've all seen this diagram in science class, right? You've got your battery, which is the power source, a wire, a switch to complete the circuit, and a light bulb to use the energy. Looks simple enough. But believe it or not, this little drawing hides a really profound secret. Let's start with that instant effect. The very moment you close that circuit, the light comes on. To make sense of this, most of us were taught a really common and pretty useful metaphor.
And yeah, that's the classic water hose analogy. It's actually a great way to start thinking about the key concepts, because it gives us something physical and intuitive to picture for something we can't even see.
All right, so just imagine your circuit is like a big loop of garden hose, and it's already totally full of water. The battery? That's like a pump pushing the water along. The wires are just the hose itself. This whole setup is perfect for getting a handle on the three big ideas in electricity.
And check out how neatly it all lines up. Voltage is like the water pressure from the pump. It's the oomph, the force doing the pushing. Current is the flow rate, how much water, or in our case charge, is moving past a certain point every second. And resistance? Think of that like squeezing the hose or having a narrow section. It makes it harder for the water to flow, just like a light bulb's filament resists the flow of electricity.
Okay, so before we move on, we got to clear up this little historical mix-up. Way back when, Benjamin Franklin took a guess. He theorized that some invisible fluid flowed from the positive end to the negative end. We still call that conventional current today. The only problem? He guessed wrong. We now know that it's actually tiny, negatively charged particles called electrons flowing the other way from negative to positive. And this is the guy who actually figured it all out, J.J. Thomson. With his work on cathode ray tubes, he proved that these little things, these electrons, were real, that they had a negative charge, and that they were the things doing the moving. So from now on, when we talk about what's flowing, we're talking about electrons.
All right, so we've got our electrons, and they're flowing through the wire just like water in a hose. And that explains the instant light, right? Well, this is where that simple analogy doesn't just bend, it completely shatters. So first thing you have to get is that the wire isn't empty. Just like that hose already full of water, a copper wire is already jam-packed with electrons. They're part of the very atoms that make up the wire. They're just there, everywhere, before you even flip the switch.
So when you flip that switch, how fast do you think one of those individual electrons actually starts to move along the wire? Get this, it's less than 0.1 millimeters per second. I'm not kidding. That is unbelievably slow. We're talking slower than a snail.
And that right there is the big mystery, isn't it? If the individual electrons are barely even crawling along, how in the world does a light bulb, maybe meters away from the switch, turn on the very instant you flip it? See, the water hose analogy just completely falls apart here.
Well, the answer, it turns out, isn't about the particles at all. The real hero of this story is something totally invisible that fills the entire circuit. It's called the electric field.
So what on earth is an electric field? The easiest way to think about it is it's like gravity, but for electricity. It's this invisible force field that a charged particle creates in the space all around it, and that field can push or pull on other charged particles, even from a distance.
And here it is. This is the big aha moment. When you flip that switch, you are not waiting for a single electron to make the long journey from the battery to the bulb. No way. What you're really doing is creating a change in that electric field. And that signal, that command to go, it travels through the wire at almost the speed of light. And this picture shows it perfectly. That super fast electric field gives a little nudge, a little shove to all the electrons in the wire at pretty much the exact same time. It's like a wave that moves through all of them at once. The electron right at the light bulb starts to move the instant the field gets there because it got pushed by the electron next to it, which was pushed by the one next to it, and on all the way back down the line. Okay, so let's take this new understanding and go all the way back to our light bulb. Let's see how it really starts to glow. All right, here's what happens. 1. The electric field pushes that whole sea of electrons into the bulb's filament. 2. Now, that filament is designed to be a bottleneck. It has super high resistance, so the electrons start crashing into the atoms inside it. 3. Every single one of those little collisions transfers energy, and that energy shows up as heat. 4. You get billions and billions of these collisions every second, and the filament gets so ridiculously hot that it glows. And boom, you've got light.
So when you boil it all down, here's the key takeaway. It's not the electrons that carry the energy. It's the electric field that delivers it. The electrons, they're just the workers on site. It's the electric field that's the boss, delivering the orders and the energy almost instantly. And that is how electricity really, truly works. Makes you wonder what other simple things have a more complex story hiding underneath.